it's my fault. Yesterday, in fact, my computer is on a different time zone, so I got confused with the time and I stopped too early yesterday. Sorry. So the lecture today will be slightly longer. I'm very sorry again. Please bear with me. It's the last one. Okay, so we were doing termination analysis, termination static analysis. We started with concrete semantics. The idea there was really just we count the steps backwards from the end of the program. Okay. So let me go back to the. So this was the concrete semantics, and then for the abstraction, what we were going to do is to abstract the concrete ranking function with a piecewise defined function. The domain of this function is going to be smaller than the concrete one. We're going to under-approximate the states from which the program terminates, and the value of this function is going to be larger, because we will over-approximate the number of steps it takes to terminate. And so the analysis works basically starting at the end of the program, creating pieces whenever we encounter new conditions, modifying the pieces when we have assignments, and then we will use a widening to predict the value of the ranking function in the pieces that we haven't seen yet. And in the end, we get an analysis that is sound but not complete. So whenever the function is defined, we know that the program terminates. Wherever it is not defined, we have an alarm. So we have a potential non-termination case, or we have a case where the program terminates. We just cannot distinguish between the two. So for the domain, we have this domain of decision trees. The constraints, we said that they are essentially linear constraints of different forms, but they are following this canonical form here. And they are totally ordered because essentially we don't want constraints, different representation of the same constraint to appear multiple times in the code. For the functions, for now we just consider affine functions, so the variables in the program, plus two special elements, this bottom and top, which both represent an undefined part of the function, but they play different roles in the static analysis. We will see in a moment what they do. So this is where we stopped yesterday. So we pick up from here. I mentioned at various times during the lectures that we have a distinction between the approximation order, which is what we use to compare the precision of different abstractions, and the computational order, which is the one that we use to compute the fixed points. So here, in this function auxiliary domain, we maintain this distinction. So we have an order, which is an approximation order between leaf nodes. So we're comparing just the leaf nodes of the decision trees now. So if they are defined, so they are not top or bottom, we use the normal comparison between leaves. So there's going to be a D element, so this D element essentially, yeah.
What's the difference between top and bottom in this one?
Yeah, so they, in terms of what they represent, there is no difference. So they both represent a totally undefined function, or at least a totally undefined partition of the function. They play different roles in the analysis. We will see later on what roles they have. But they also play a different role in this, between the approximation and the computational order. We will see later why. But the idea is basically, okay, each leaf is identified by a piece of the tree. So a partition of our function is where the leaves are. So this element D here is whatever partition of the function we are in. So we essentially collect all the constraints down to the leaf. And we build this abstract domain element which represents the piece where we are. So within that piece, we compare the functions when they're both defined, two leaves are both defined. We compare the functions in those environments. When one of them is undefined, we use this order here. So essentially anything that is defined is going to be more precise than anything that is not defined. This is for the approximation order. For the computational order, what changes is just what happens with the undefined nodes. For the computational order, so again, this is where, this is for the approximation order. So here we talk about the precision of the analysis in a sense. So whatever is undefined is going to tell us less about termination. It's going to tell us nothing about termination, in fact. And that's why these are at the top. Okay? So both bottom and top, with respect to termination, they mean nothing. It means that the program doesn't terminate. Yeah.
And just to recap one last time to be sure, the function is going to take us from labels to distance from termination? Or?
Yes.
Okay.
The function basically tells us, this function here will tell us at this particular label in the program, it will take us at most this many steps to terminate.
Okay.
So anything that is defined here, it really means we are at this many steps of termination, we can prove termination from here. For the computational order, this is the order that we use to actually build the function during the analysis. So we're going to start with an undefined function, we're going to make it defined, and in some cases we will lose precision and it will become undefined again. Again, we will see later what I mean. So, for the functions now, we are done with the functions, we are done with the constraints. We can now define what this tree represents. So the trees they have leaves, or they are nodes with the constraints and two-step trees. And so essentially what the concretization function does, so the concretization will map a tree back to a function, a ranking function in fact. And so what this concretization function does, I mean it's very ugly to read, but essentially what we have to do first is to go down to the leaves by collecting the constraints that we encounter. So essentially, let's say we have a node with a constraint at the node. We will go on the left, collecting the constraint itself. On the right, we will take its negation. Okay, this will be collected there. When we get to the leaf, we have a whole bunch of constraints that we collected. This will identify the piece where the function is defined. Yeah.
In this case, negating the constraint means, so is the constraint something like we will terminate within 5?
No, this is the constraint on the value of the variables. We will say x is less equal than 10. This is really identifying the piece of the function. So in the figure here, this will say, okay, if x is greater or equal than 0, then we go down here, we terminate in 5 steps.
Okay.
Otherwise, we are in this case, so this is the case where x is equal to 3, for instance. We are here, we terminate in 9 steps. So all these paths essentially will identify the various pieces of the ranking function. Okay, so, right. So this one basically here will tell us in which piece we are. And now at this point we use the function, the concretization of the function to know how many steps it takes to terminate from that piece. And so we are, whenever we have bottom or top, we said this is just undefined, we cannot prove termination here. And for everything else, we just evaluate the function in that case. Good. So this is what the trees represent. And now, how we manipulate the trees. We have a lot of operators to go through. This is actually a very complex absolute domain. I just wanted to present it to you because it's like a real example of an absolute domain, in fact, with everything that has to go with defining an absolute domain. So now, for these operations, in fact, they work on trees plus the special elements nil. So these are trees that don't exist in a sense. So it's like a placeholder for a tree that is not there. We will see why we need them later on, but essentially with some operations we will need to cut away some part of the tree, and so we will need to put a placeholder there because we will need to merge with other parts of some other trees. So in an absolute domain, we have seen them in simpler examples. We have various operations that we need to define. We have to define a way to compare elements of the decision tree, of the absolute domain, sorry. And in particular, since we have different orders that we're dealing with, we have two different ways to compare the elements. It's going to be an approximation order on trees and a computational order on trees. Similarly, since we have different ways to compare the elements, we also have different ways to merge the elements together. So we're going to have an approximation join and a computational join. For intersecting the trees, in this particular case, we just have one operation. And then we have this widening operations that will try to guess a ranking function from two trees that we have seen. And then finally, we have this unit operators to deal with assignments and conditions that appear in programs. So we have an assignment operation. It's a backward assignment operation because the analysis goes backward through the program. And we have a filter operation. The filter basically takes a condition in the program, will prune away parts of the tree. Okay, yes. And the binary operators, since we have to operate on 2 trees at a time, which may work on different partitioning, they may represent different piecewise defined functions. We need to basically unify them. We need to define this 3 unification algorithm. We'll try to find a common piecewise definition for the functions that we are trying to merge or compare. So I will present you the 3 unification. I want to go through the 3 unification because we also need it in the widening, because in the widening we will do a variant of the 3 unification to do the actual widening. And we'll see later. So, again, the unification is to try to find a common refinement between 2 given decision trees, to then do some other operation on them. So the base case is when we have descended to the leaves, we are comparing 2 leaves. So let's say we have 2 defined leaves. These are the 2 trees that we're comparing. Let's say we have 2 leaves that are completely defined. The unification will just not do anything. We're done. Same here. If it's a leaf and some placeholder nil node, nothing happens. And so that when we have descended the leaves, essentially the unification is already done. The difficult cases are when we are trying to unify a leaf with a node that has a constraint, or 2 nodes, essentially where the constraints are not the same. Okay. In this case, we have various cases that we have to consider, depending on whether the constraint that appears in one of the nodes is redundant or not with respect to the trees that we already have built. Because it could happen that essentially there is a constraint. Let's say here, this constraint, in the easy case, in a sense, at the beginning at least of the unification, the constraint is missing from here. What will happen is that we add it essentially to the, well, okay, it's not, okay, fine. We add it to the first tree, or in this case to this leaf here. But in other cases, it could be that we added already enough constraints that whenever we try to add another constraint, it becomes redundant, either the constraint itself or its negation. So in those cases, let's say here, C2, it's present here, but we don't actually need to add it because it became redundant now. We don't actually add it. We're just going to go down to the left-hand side of this tree, the left subtree of this tree, and continue the unification with the leaf. Vice versa, if the negation is redundant, we just go on the right-hand side. In the case where we have 2 constraints, but one of them is comes before, remember the constraints have to be totally ordered. So if the C2 constraint should actually appear before the C1 constraint, and it's not redundant, then we just add it. So we put it there, and then we continue with the tree that we have on the left. So C1 in this case, or the leaf in this case, and we continue the unification down. Yeah.
When do we throw away L2 and R2?
They're not thrown away. So this, sorry, they have the same name. We are basically saying, okay, we add C2, and then we continue the unification with C1 and the subtrees, and L2 on the left. And for the right subtree, we continue with this tree, which is here, and with the right subtree.
Oh, so you'll try to unify those?
Yeah, we're going to continue down the unification. We're going to start at the root, trying to match it. I have an example in a moment, it will make more sense. But yeah, we start at the root, we try to match it, and then we continue down to the subtrees. The other cases are, well, the other case is the symmetric case. And it can also happen that we have the same constraint on the trees, but since we added other constraints earlier, then this constraint may become redundant, so we just essentially ignore it and continue down, or we just keep it and we continue to the subtrees. I'll show you the example, will be better probably. So these are the 2 trees that we're trying to unify. I'm keeping, for instance, this placeholders for some parts of the tree that we can ignore, or is missing at the moment. So here we have 2 trees with 2 constraints that are different. Now I don't remember which one goes first. Okay, this one is smaller than this one for whatever order that I picked in this example. So we have to keep this constraint and continue the unification down with the rest of the tree. So we're going to keep the constraint. So we're going to, again, build two trees. So we're going to modify the two trees to be unified. So this tree will keep this constraint. This tree will add this constraint. Now what happens is here, the constraint is there. So we descend to the leaf. And now we have to unify this tree with this leaf. This tree, there is a constraint that is now redundant because the fact that x is greater or equal than 0 subsumes the fact that it's greater than -1, so we ignore it. We descend to the leaf, we unify these two leaves, so now we're going to have this leaf remains here, this is the base case in the other leaf. On the other side, we have to unify this leaf with this tree. Now this tree is not this constraint now is not redundant, so we're going to add it and then descend to the leaves as before.
So, two questions. One is, so each label in the program has an associated tree.
Yes.
Okay. And when would you get two different trees? If you do like two approximations and you're combining them? Or?
You could, for instance, do an if then else. So you go through one branch, you go to the other branch, and then you have to figure out a ranking function that holds for both possibilities, essentially. Okay. So then you're going to merge.
And the last confusion I have is this unification seems to make two trees instead of unifying them into one.
So this is just the first step that you need to do before you do any other operation.
Okay.
So first you unify them, and then you can merge them, or you can compare them, or do whatever. There was some other.
I have the same question.
Okay, good. Yeah, so now that we have unified them, we can actually do the operations. For instance, we can compare them. So how does comparing two unified trees work? Well, first of all, comparing two trees, we have to first perform the tree unification. Then we have to go down the trees. We have to go down the tree, following all paths down to the leaves. And we have to collect all the constraints, because essentially we have to reconstruct the pieces in which the leaves live. And then when we are at the leaf, we're going to use the approximation or computational order, depending on how we want to compare them, that works on leaves. Good. This is just for comparing. Of course, well, a nice property to have is that the comparison function is monotonic with respect to the order. In particular, with respect to the approximation order, we don't care about the computational order for the comparison. So essentially, is what this result says is that if you have two trees that are comparable, and like this T1 is less precise than T1 in the abstract, you're also going to get something that is less precise than the first one in the concrete. Essentially, this is what's inside. So with this order here, the concretization function is monotonic. For the join, then how does it work? Again, similarly, we have to go down the tree and create the constraints. In case of nil nodes, it's the non-placeholder tree that wins. So any nil node is replaced by the counterpart that is not nil. And then at the end we compare with the join. How does the join work? I didn't tell you earlier. The join is essentially trying to find a function that is above any two that you have on the leaves. So, I mean, there is a sort of an informal definition, but the idea is, maybe you can look just at the example to get the idea. If you have two defined leaves, this will tell you how many steps it takes to terminate from that partition of your set of environments, memory states. Okay? So this will tell you it will take this many steps to terminate from here. This will tell you how many steps it takes to terminate from here. When you merge the two functions, what you want is something that is larger. We have to do the max between the two functions. But the max may not be, so for instance here the max will be this line here. Sorry, people on the other side cannot see. These two lines here. But this one, in that partition, is not a linear function, an affine function that we can represent. So essentially what we do is find a linear function that is above the maximum. So that the smallest linear function, yeah.
Is there a lot of error if like if their angle is very acute between the two of them?
Yeah, so it could be that in fact you cannot find a function that you can represent. So imagine these lines extend to the entire space. There isn't a natural value function that can approximate them. So then you end up with saying, well, for instance, you would say top, I don't know, if it terminates or not. If you can handle ordinal value functions, we'll see if we have the time to see them. In that case, you will put an omega there and then continue from there. Yeah. So, in any case, we essentially do a sort of a convex hull between whatever downward function we can have and take the line that is above. This is between defined functions. For undefined functions, we follow the diagram. So whenever there is a component that is undefined, we keep the undefined component. This is because we're doing definite terminations. So it's one branch of our program says that we don't know if the program terminates. We have to be conservative. And so we have to say, well, we don't know which branch we're going to take, so we don't know if we can terminate from this point onwards. That is the reason why we follow this order here. So in the example, yeah.
What happens if they're both undefined in opposite ways? Like if one is bottom and the other
So the way it is constructed, it cannot happen.
Oh.
Yeah, it's done such that they're not comparable, in fact. So it's constructed in a way that it doesn't happen. Actually, I haven't proven that it doesn't happen, but I'm fairly confident that it doesn't. So in the example, well, these are the trees that we have unified before. Now when we merge them, you see it's easy. They have the same structure. So we have to basically just have to go down to the leaves and merge each leaf with the corresponding one. So here there is a defined leaf with a nil node remains defined. Here we have a defined leaf with something that I haven't specified, so we just do the whatever join here. And this is another nil node with something else, and we keep this something else. This was for the approximation join. For the computational join, same story roughly, at least for the defined leaves, but for the undefined ones, we keep the defined one. So this one, when do we use this computational join? This can happen, for instance, when we do the wedding, the iterations of the loop. So what we're going to do is that we're going to essentially say, okay, we found a new partition where the program is terminating, which we didn't know that it was, we didn't know anything about before. So we will end up in a situation where we're merging something undefined with something that is now defined. And so we keep the defined one. This is the new information that we have. This is when we use the computational join in fixed point essentially. Okay, so for the meat is very similar. We are going to do, it's very confusing because we do the approximation join of the leaves. The only difference is that when we merge nil nodes and other trees, we keep the nil nodes. The meat is essentially, let's say we are doing an if then else, and we have a Boolean condition that is an AND. So one part of the, so it's an A and B. When we filter with the expression A, we're going to throw away some parts of the tree. When we filter with the expression B, we're going to throw away some part of the expression B, for expression B. And now when we merge them together to do actually when we intersect them during the meet, when we do the end, we're going to have to keep, to throw away basically anything that has been thrown away by other expression has to be thrown away. So meet, in the example from before, we'll keep the nil nodes and we'll merge together the two ones that are not known. Okay, now there comes the complicated part, which is the widening. The widening will take, I don't know, 10 slides, I think. So you have to be very, very patient. Okay, the problem with the widening is that the goal of the widening is to try to predict a ranking function. Maybe I can show you, okay, maybe before I talk about the widening, I want to show you the example so that what I'm saying will make a bit more sense. So let's consider the example here. So we have now, we are reading a variable x, we are picking some random value, non-deterministic value, sorry, it's not random, between minus infinity and plus infinity. Same for y, and now while x is positive, we decrease the value of x by the value of y. So we do x equals x minus y. Now if x is 0, if y is 0 or it is negative, I think, we don't terminate. So it doesn't always terminate this program. So what we want is to find the ranking function that will tell us when the program terminates. So the way the analysis works is that we start on the set at the end of the program. So this is the tree that we have. So it's just a leaf. And I'll show you where the leaf is defined. So this is the space of values of program variables. It's defined everywhere for any possible values of x and y. We are at value 0. Okay, I haven't told you what the filter does yet. I'll just show you in the example. You will see later the actual definition. What the filter does is basically adding the constraints to the tree and counting new steps to termination. So first of all, we have to count one more step to termination. We have to do this filter here. We have to actually check if this condition holds. So this is one more step to termination. And then we add this constraint, because this one step to termination is only if the condition doesn't hold. So if the constraint is not true, so if the boolean, the guard of the while is not true, then we are at one step to termination. Otherwise, we don't know yet. So that's where the placeholder happens. Okay, now we have to basically merge this tree that we have constructed with the filter with whatever we know about the inner side, the inside of the loop, which is nothing. We have anything, nothing is defined there. So essentially, at first, what we have is just this. So it's 1 if we don't enter the loop, and undefined otherwise. So here, what we're saying is that if we never enter the loop, we are at one step to termination, and for the rest, the program may not terminate. We have no idea. Then we continue the analysis from there. We have to continue to program point 4. Here with the assignment, again, I didn't tell you what the assignment does, but essentially, it's actually quite easy going backwards to do assignments because they are just variable substitution, essentially, most of the time, at least the easy assignment. So here we are, again, we have to count one more step to termination. So we're going to do 2 steps to termination, and we're going to replace x with the expression that we are assigning to x. So x becomes x minus y. So this piece of ranking function here is modified into this green piece here. Sorry for people on the other side, this green piece here. So, okay, and now we go back to the filter here. Yeah. So we have to go back from program point 4 to program point 3 from inside the loop. So this will give us this other tree here. Actually, I've done the join already with what we had before, so I skipped some steps. But essentially, we add this constraint again. If we are within the loop, again, we don't know anything. Yeah. No, okay, sorry, never mind. This means, okay, if we enter the loop only once, we are at 3 steps to termination. We're going to enter, check the condition, enter, this is 1 step. Do the assignment, 2nd step, check the condition, 3rd step, and then we're going to exit. So this is 3 steps to termination. Yeah, this is just the filter, I haven't done the join yet. Otherwise, it is undefined. This part here remains undefined. For anything else, from outside of the body of the loop, we don't know anything yet. Then we have to merge the 2 trees. So we have this tree. This is coming from outside. This one. This one is coming from inside of the loop. We merge them. We do the join. The join we have seen how it works. And so here we have basically 1 step to termination if we never enter the loop. 3 steps to termination if we enter the loop once. Let's say we do the analysis again of this loop. We're going to have this tree. Okay, this will tell us, okay, now we know that if we never enter the loop, we terminate in 1 step. If we enter once, we terminate in 3 steps. If we enter twice, we terminate in 5 steps. And now basically I have to guess what happens if we enter n times, or whatever number of times. This is where the widening comes into play. Problem is, the widening can be completely wrong, because we have no idea how to do it such that it is smart enough to not be wrong. So let me go back to the widening, and I'll tell you how it works. So what it means for the widening to be wrong? Well, it could be that it is just making a wild guess and adding states to the domain of the function from which the program is not actually terminating, or vice versa, it could underestimate how many steps it takes to terminate. So there are different ways to be wrong for the widening. So I made this small example here. So let's say this is the concrete ranking function for this transition system. So here we are 0 step to termination, 1 step to termination, 2 steps here, 3 steps here. All of these white ones here, they don't terminate. So let's say now, with the analysis, we found all of these points, 0, 0, 1, 1. And now with the widening, we decided to just guess that all of the states here are inside of the domain of the function. And from all of the states here, we will terminate in 2 steps. Now this is wrong for various reasons. This one is a state that directly doesn't terminate, it's directly on a loop. This one is a state from which we can reach a loop, an infinite loop. And this one is a state from which program terminates, but we underestimated how long it takes to terminate. So there are these 3 different ways to be wrong. So how the widening works is that it does 4 different things. So first of all, it has to check, so the widening will essentially enlarge the domain of the function and enlarge the value of the function. But before it can do that, it first has to check if it made the wrong domain prediction. So essentially, if it has included states that lead to a non-terminating execution, so, which is this case A here. If that is okay, so it checks if he has done that. If he has done that, then it will fix it. I will show you how it's fixed. After he can do that, after he has done that, so all the domain is okay, it will do a domain widening, so it will enlarge the domain of the function. And then we will check if there are wrong value predictions. So you can argue that C is actually a wrong domain prediction, because it is a state that doesn't terminate. But in fact, we detected in this way, because we detected, we will see, by a function, we will notice that the function increases its value between iterations, and this is how we detect it. So the B and C case will behave analogously in a sense. So we will see that the value that we predicted for the function is wrong. We will fix that, and then we can finally do the value widening that we wanted. So feeling ready to see how that works. So how do we check for the case A? The check for case A, so the important bit is that all the operations done by the domain are correct, are sound. So they will not do anything wrong.